Today, we will look at the firm's problem from a different perspective, that of finding the least cost way to produce a given level of output. We call this problem the firm's cost minimization problem. By the end of this lesson, you should be able to set up and solve a firm's cost minimization problem. The solutions to this problem will be the firm's conditional factor demand functions for its inputs, which you should be able to derive as a part of solving the cost minimization problem. In addition, you should be able to derive a firm's isocost lines on your way to solving its cost minimization problem. After solving the firm's cost minimization problem, there are a number of predictions and explanations that you should be able to make. First, you should be able to predict the effect of changes in input prices on the optimal quantities of inputs that a firm will use and explain why these predicted changes make sense. In addition, you should be able to explain the relationship between profit maximization and cost minimization. Finally, you should be able to explain the differences between fixed costs, quasi-fixed costs, and sunk costs, and explain the relationship between returns to scale and a firm's costs. Let's start out with a simple proposition. If a firm is maximizing its profits, then it is automatically minimizing its costs. Why is this the case? If a firm isn't minimizing its costs, then it could earn higher profits for the same level of output by choosing the least cost method to produce this output. Therefore, profit maximizing firms are, by definition, cost minimizing. Before we begin examining the firm's cost minimization problem, let's consider the types of costs that a firm can face. There are 4 types of costs. First are fixed costs. Fixed costs are the costs of a firm's fixed inputs. The firm has to pay these costs whether or not it produces any output. Because the costs are fixed, they do not change with a firm's output level. An example of a fixed cost would be the firm's payments on the loan it uses to finance the construction of its factory. A quasi-fixed cost is a cost that is 0 if the firm produces 0 output, positive if the firm produces positive output, but otherwise does not vary with the level of output. An example of a quasi-fixed cost would be a setup cost for a machine before it is used to produce any output. A sunk cost is a cost that a firm has already spent and cannot recover. An example would be the purchase of a specially designed machine that is useful for only that firm. If the machine has no resale value, then the entire cost of the machine would be a sunk cost, because no matter what the firm does, it cannot get that money back. If the machine can be resold, for example as scrap metal, then the initial cost minus the resale value would be the firm's sunk cost. The final type of cost is a variable cost, which, as the name implies, is the cost of the variable inputs into a production process. Variable costs increase as the level of output increases. Examples of variable costs include items like labor and the cost of the materials required to make a firm's product. Before we continue, we will make one assumption. When analyzing the firm's cost minimization problem, we will assume that the firm is operating in the long run. Recall that in the long run, all costs are variable. This thought exercise has provided us with another way to think about the firm's profit maximization problem. Instead of thinking about it as a single problem, we can break the profit maximization problem into 2 steps. The first step is to determine the least cost input combination to produce a given level of output. Then, determine the profit maximizing level of output. We will consider the first part of this problem today, the cost minimization problem. We can describe the firm's cost minimization problem as follows. The firm wants to minimize its costs, which equal the sum of the price of each input multiplied by the quantity of each input that the firm uses. Obviously, the minimum value of this function is 0, but when costs are 0, the firm is not producing any output. So, the firm wants to minimize cost to produce a given level of output, which is described by its production function. Therefore, the firm is minimizing costs subject to its technology constraint. One way to approach the firm's cost minimization problem is graphically. Consider the firm's cost equation. What would a graph of this function look like? For any given cost level, the graph of the cost function in x1, x2 space will be a downward sloping line. There will be a different line for each possible cost level that the firm could have. These lines are called isocost lines. Isocost lines for higher cost levels will be to the northeast of isocost lines for lower cost levels. We could also put an isoquant into this same graph. Remember that the isoquant represents the technology constraint, the amount of output that the firm wants to produce. Graphically, the firm's cost minimization problem boils down to finding the point on a given isoquant that corresponds to the lowest possible isocost line. Hopefully, you see some similarities between this problem and the consumer's utility maximization problem that we studied earlier. First, the cost equation is equivalent to the consumer's budget constraint. Second, the production function and the utility function are equivalent. The difference is that in a utility maximization problem, the utility function is the objective function and the budget line is the constraint. In the firm's cost minimization problem, the roles of the two equations are reversed. The cost equation is the objective function and the production function is the constraint. You may recall that the solution to the utility maximization problem was the point where the budget line was tangent to an indifference curve. Similarly, in the firm's cost minimization problem, the cost minimizing input combination will be located at a point where the isoquant is tangent to an isocost line. It is easy to see that the lowest possible isocost line that touches this isoquant is the isocost line that is just tangent to the isoquant. Thus, this point represents the cheapest possible way to produce this level of output. Therefore, the input combination x1 star, x2 star represents the input combination that the firm should use in order to produce y1 units of output at the lowest possible cost. The solution to the firm's cost minimization problem will describe the amount of each input that the firm should use as a function of the prices of the inputs and the level of output that the firm wants to produce. These functions are called the firm's conditional factor demands for inputs 1 and 2. They are called conditional factor demand functions because they describe the firm's demand for each input conditional on the amount of output it wants to produce. What is the difference between the conditional factor demand functions that we derived from the firm's cost minimization problem and the factor demand functions that we derived from the firm's profit maximization problem? The conditional factor demand describes the optimal amount of each input that the firm should use as a function of both input prices and the quantity of output that the firm wants to produce. The factor demands describe the optimal amount of each input the firm should use as a function of the prices of the firm's inputs and the price for which it can sell its output. If we substitute the firm's profit-maximizing level of output as a function of the price of output into the conditional factor demand functions, the result will be the factor demand functions. We will see how to do this in a later lesson. Now that we've seen how to use graphical analysis to solve the firm's cost minimization problem, we will work through an example using calculus. Let's start by setting up the problem. The firm's goal is to minimize its costs, so its objective function is the cost equation. The firm doesn't want to minimize just any costs, but the cost to produce a particular level of output. So the constraint is its production function, which describes how much output a firm can produce with a given quantity of inputs. Now that we've set up the problem, let's consider an example. Let's let the production function be f of x1 and x2 equals 3 times the square root of x1 times x2. In order to solve this problem, let's think back to how we solved utility maximization problems. The first thing that we did was to solve the constraint for one of the choice variables. We will do the same thing here. In this case, the constraint is the production function, so we want to solve it for either x1 or x2. I will solve it for x2. When we work through the algebra, we see that x2 equals output squared divided by 9 times x1. Then we substitute this solution into the cost equation. Now that we have incorporated the constraint into the objective function, we can use calculus to find the value of x1 that minimizes this function. To do this, we will take the first derivative of the cost equation with respect to the remaining input and set the derivative equal to 0. Then we solve for x1. When we do this, we find that the firm's optimal quantity of input 1 equals output divided by 3 multiplied by the square root of the price of input 2 divided by the price of input 1. This result tells you the cost minimizing amount of input 1 that the firm should use to produce output level Y when input prices are W1 and W2. Let's pause for a moment to take a look at this solution and see if the results are consistent with our economic intuition. First, what happens to the firm's optimal quantity of input 1 when output increases? From looking at this equation, we can see that the firm will use more of input 1. Hopefully, this matches your intuition that if the firm wants to produce more output, it needs more inputs. So this part of the conditional factor demand function is consistent with our economic intuition. Second, we could ask what happens to the firm's quantity of input 1 as input 1 becomes more expensive. Again, we can see from the function that as W1 increases, the quantity of input 1 that the firm will use will decrease, since W1 is in the denominator of the conditional factor demand function. This should match your intuition as well. As an input becomes relatively more expensive, the firm should use less of it. Finally, we could ask what happens to the firm's optimal quantity of input 1 as the price of input 2 increases. From looking at the equation, we should see that as input 2 becomes more expensive, the firm uses more of input 1, since W2 is in the numerator of the conditional factor demand function. This should match your intuition as well. As input 2 becomes more expensive, the firm should substitute away from it and use more of input 1. Therefore, our solution appears to pass the sanity check. The last step in the process is to substitute our solution for input 1 into the equation for input 2 that we obtained in step 1 and solve for the conditional factor demand for input 2. Although I could work through the algebra for this, I trust that you can do it on your own. To check your answer, you should find that the conditional factor demand for input 2 equals output divided by 3 multiplied by the square root of the cost of input 1 divided by the cost of input 2. Because this solution is just the same as the solution for the conditional factor demand for input 1 with the input costs reversed, we know that this solution will also pass the sanity check. There is one other method that we can use to solve the firm's cost minimization problem. This method takes advantage of the fact that at the cost-minimizing input combination, the isoquant is tangent to an isocost line. This means that at this point, the slope of the isocost line and the slope of the isoquant are the same. The slope of the isoquant is the technical rate of substitution, or TRS, and the slope of the isocost line is the ratio of the input prices, negative W1 over W2. For this reason, we will call this method to solve the cost minimization problem the TRS method. Not surprisingly, the first step in the TRS method is to calculate the firm's technical rate of substitution. You should recall that the technical rate of substitution is the ratio of the marginal products, which for this production function is simply negative x2 divided by x1. Step 2 is to set the technical rate of substitution equal to the ratio of the input prices. Step 3 is to solve for one of the inputs. I will solve for input 2 as a function of input 1. Step 4 is to substitute this solution into the production function and solve for the input. When we do this, we see that we get the same answer for the conditional factor demand for input 1 that we got before. To finish the problem, substitute this solution back into the expression for input 2 from step 3 and solve for the conditional factor demand function for input 2. If we substitute the conditional factor demand functions for inputs 1 and 2 back into the cost equation, we get what is called the cost function. The difference between the cost equation and the cost function is the cost equation tells you the cost of using any input combination, including all those combinations that do not minimize costs. The cost equation is a function of the prices and quantities of the inputs that the firm uses. The cost function tells you the minimum amount it will cost the firm to produce a given level of output. It is a function of the input prices that the firm has to pay and the level of output that the firm produces. Continuing with our example, if we substitute the conditional factor demands for inputs 1 and 2 into the cost equation, we get the firm's cost function, which equals 2y times the square root of W1 times W2, all divided by 3. There is a relationship between the nature of a firm's production and the nature of its cost structure. If a firm has constant returns to scale, when all of its input double, its output doubles as well. Because a firm has doubled its inputs, its cost should also double. However, since both output and cost doubled, per unit costs are constant. This leads us to the general result that firms that have constant returns to scale in production will have constant per unit costs of production. If a firm has decreasing returns to scale, when it doubles its inputs, its output less than doubles. Since its costs double, but its output less than doubles, its per unit costs go up. Thus, firms that have decreasing returns to scale in production have increasing per unit production costs. Finally, if a firm has increasing returns to scale, if it doubles all its inputs, its output more than doubles. Since output more than doubles, but costs are only twice as much, the firm's per unit costs are lower. This leads us to the general result that firms that have increasing returns to scale in production have decreasing per unit costs of production. We can see the relationship between a firm's returns to scale and its per unit production costs using the example that we have been studying. This firm has constant returns to scale in production. To find this firm's per unit or average cost of production, divide the cost function by y. When we do this, we see that the firm's average cost of production are 2/3 times the square root of W1 times W2. This number is constant for all levels of output, verifying that this firm with constant returns to scale in production has constant average cost of production. This concludes this lesson on cost minimization. You will have a chance to practice more examples like this in class.